Welcome. In this session in linear data analysis, we'll explore Kernel PCA. This is a way that we can use an embedding without actually calculating the embedding, and we can perform principal components analysis using a gram matrix. So a question with PCA is, normally we present this with variables, but could we also use observations? Well, that turns out to be a very valuable line of inquiry. So what we were doing was we were given M observations in a data matrix, and we embedded each row in a higher dimensional space. If we tried to use PCA variable style on this, we would be using a variable style scatter matrix, and this would have a size of P times P, and that could be extremely large. So recall that P will grow combinatorially for a polynomial kernel with the order of the polynomial. So let's recall the gram matrix. The gram matrix was a weight matrix, a generalized weight matrix, and we put a hat over it. And it's a square matrix, it's symmetric, positive, semi-definite, and it has the same number of rows as our data have observations, and now the number of columns have to be the same as the number of observations. And we can compute each entry of this gram matrix by using a kernel function, which is a symmetric positive semi-definite mapping. And this takes two observations and it returns a real number. And so now we can explore this alternative of using the observation style scatter matrix that is associated with the embedding. And the valuable thing that we understand from a previous session is for PCA, it doesn't matter whether we use variable style scatter or observation style scatter. We're going to get the same answer. So let's try working this out. So what we have here is our scatter matrix defined using observation style. We would represent that as the zero mean embedded times the zero mean embedded transpose. Well, that's not exactly what we want to do, right? So this is wrong. Let's put a question mark over that and say that that's wrong. What we want to do is we want to say that the observation style scatter matrix is, what we want to do is we want to take our data, embed the data, take the transpose of that, and then this matrix we want to center. So we want to use our centering matrix for M rows, and then on this side we would take that and transpose it, although if we were doing computations, this is a symmetric matrix, so we're writing this out so that we can get some clarity here. So that is the centering matrix times the gram matrix, which is a generalized weight matrix, times the centering matrix again. And this means we never need to embed. And let's put an exclamation, because that is the kernel trick. So instead we compute each entry of ij of this gram matrix, and we do that using the kernel function. So this gives us Kernel PCA. So Kernel PCA, and this process is, we simply take this matrix, this observation style scatter matrix that we compute by we find the gram matrix and then we center it, and what we do is we do a spectral decomposition. And we would usually write the orthogonal matrix as Q. For clarity, let's write this as U hat, because this is coming out of the singular value decomposition. And then this will be times some lambda hat, which is a diagonal matrix that has the eigenvalues, times U hat transpose. So this matrix is symmetric positive semi-definite. That means it's guaranteed to have a spectral decomposition, and the spectral decomposition must look like this. That means that our kernel scores are, we would form a kernel score matrix, and that would be the left singular vectors from the SVD of the centered scatter style object times the singular values that come out of the SVD, and we have this. So the computation, computation is slower than PCA, and the reason is because the number of observations in data typically far exceed the number of variables that we have in our data.